Thank you. Thanks, Phil, for inviting me. I've heard so many good things about this meetup, and the turnout is incredible. So I'm really excited to be here. And today, I'm going to be talking about something that's highly relevant to what I'm working on now, but also what I worked on while I was working at MotherDuck. Just some things that I've been thinking about, summarizing, and wanted to share. It's nothing too serious, but more just sharing my thoughts over the last few years of working on database systems. And maybe you've guessed it from the title. This talk is going to be a bit of a critique, both on the rush towards microservices and the rush towards distributed systems in general. Because sometimes what you need is not a bunch of gRPC microservices running on Kubernetes. And instead, what you need is a single, testable, local system. And we'll think about why that is the case. Cool. So a little bit about myself. As introduced, my name is Stephanie, and I'm a staff software engineer now at MongoDB. I've been here since March this year, so I'm relatively new. And before MongoDB, I was at MotherDuck, and we built a cloud data warehouse system based on DuckDB. So how many people know about DuckDB? Oh, wow, awesome. So I guess you already love local systems, so that's great. So what motivated my talk today? So lately, we've seen quite a rise in interest of these distributed systems that are revolving around in-process, in-memory databases. So for example, DeepSeek's very famous small pond, that's basically distributed DuckDB. And from a different meetup, I learned about data fusion for Ray, which is basically distributed data fusion, another in-process, in-memory database. These projects are getting quite a lot of buzz, but actually, let's be honest, this is not a new trend. For a long time, perhaps decades, going distributed has been a go-to move for system builders because they think that things will get big or might get big one day. And this one is my favorite that I just saw very recently, maybe 2 days ago, randomly on LinkedIn. I never check LinkedIn comments. This is one time I checked, and this person is advocating for a distributed MCP server. Awesome, yes, we need that, obviously. For what reason, I don't know. But I don't know if you've spotted some of the anti-patterns. I've summarized a few. So there's something I would like to call the DevRel stack. So basically, a system built entirely from popular open source projects without checking if every component is actually needed. One of my friends shared with me this system. Let me try to remember. It's a query execution engine. And the compute layer alone is composed of linked SQL, so maybe multiple data sources, and then calcite, and then substrate, perhaps for interoperability of query plans or something. And then the substrate connects to some type of custom planner, maybe for system specific query optimization, physical planning, whatnot. And then that connects to Ray, and that connects to Velox. And that's only the compute layer of things, not the storage layer. So things like that, right? It's cool, but can that be simplified? Maybe. Another thing is production paranoia. Basically, scaling for an imagined 1 million query per second. Because when you're still in private beta mode, when you have maybe like 10 real enterprise users, maybe 100 small users, but you're imagining something, that might happen. I mean, awesome, but I don't know. And next thing is tiny data, big infra. This is actually more common than you think. So basically using distributed compute for jobs that could easily fit in RAM and you can just run a loop for. But people want to use distributed systems for that. And the last one is monitoring the monitoring. So you have a bunch of dashboards, let's say 5 dashboards, but you still don't really know whether your model has improved or how your system is breaking, because you're just building more and more Grafana dashboards, because why not, right? More metrics is always great. So these anti-patterns didn't come about because people were aiming for these. I wanted to complicate my system so it becomes that way, it becomes hard to maintain. That's not the case. People oftentimes build systems with very good intentions, but then somehow end up in a tricky spot. And it's really not the system builder's fault. Because if we go back in time and think about when microservices came into the picture in the early 2010s, people had real struggles around managing tightly coupled monolithic applications. So what people want to get is breaking things up a little so teams can have more autonomy, right? And you can deploy different components independently. But is that what actually happened, right? And what we got instead, the promise was microservices and distributed systems give us clean boundaries and scale. However, more moving parts also mean more breaking points, right? So your developers now need to also understand infrastructure, not just the code itself. And your local development becomes very difficult because in order to test something, you need a local stub, you need mock, you need Docker compose hell. And oftentimes people start to ask the question, what does this service even do? And that's not even a very uncommon question, right? So instead, you didn't remove the complexity, and you just moved the complexity to the communication, the network layer. And in the end, your system is actually harder to debug. And the next thing, the promise was horizontal scaling will give us better performance. That makes sense, right? If you think about it. But every single network hop adds tens of milliseconds of latency. And your tail latency is the number of microservices that are chained together. And your slowest microservice determines your responsiveness of the system. So if your user clicks search, and that hits 5 different microservices, and one of them restarted, your system now hangs, and you have no idea, which part, and you have to spend a lot of time trying to debug it, right? So your system sometimes can actually end up getting higher latency overall. And the next promise, cloud-native infrastructure is resilient by default. However, a single schema mismatch could bring down your entire pipeline because your systems now cannot really talk to each other. And deployment order matters as well. Your staging and production can drift out of sync. And your Kubernetes add multiple layers of complications as well. And sometimes you have to manage config drift, cluster scaling, challenges, and all sorts of different caching problems. So with monolith, one thing failed. But with microservices, everything can fail together or independently. So in the end, your system is actually more fragile. The next one. The promise was, we'll use tracing and metrics to debug faster. Yes, you can absolutely do that. And distributed tracing will give you the information, but of 30 microservices. So good luck on finding the trace that's actually relevant to the problem that you're trying to solve. And now you have 5 dashboards, and you still have no idea what's actually breaking your system, because most dashboards are alerting on system-level signals like CPU usage, memory usage, disk usage, and things like that. And they don't actually alert on anything related to business correctness. So in the end, you have worse developer experience. And the next one, microservices will let us focus on the important stuff, clean separation of concerns, reusable components, and rapid iteration. Ideally, but the reality is you spend most of your time wiring up Kafka, trying to tune your Kubernetes resource limits, fix your CI/CD broken builds, right? And debugging and managing Docker image versions, and then still wondering why your server cannot deserialize its inputs. And your actual application logic that's in your system is maybe 200 lines of real logic code, but that's being buried under thousands of lines of infrastructure. And then what happens is you're trying to build a system that maybe returns 5 top search results, right? However, most of the time, 90% of the time is probably spent on just making sure your data is moving correctly from container to container. So in the end, you end up facing more infrastructure glue and then dealing with your actual business logic. So now you got to scale with all of these cool technologies, but you've lost the simplicity, and you end up paying the new complexity tax. So now let's think about it. What are some of the actual building blocks that we need to build a system that needs to scale? So let's do a thought experiment of building a semantic search system using embeddings. So let's say you're now asked to build a semantic search system for 100,000 product reviews. 100,000, why? Because this is not a toy-sized data set. Right? This is actually a pretty relevant data set for a medium-sized company. It could be a niche e-commerce company or some type of product with internal feedback or user reviews. So let's say the goal is so that users can search using natural language and get relevant semantic matches from your system. So let's assume that each review is roughly 1 kilobyte, and the embedding is 768 dimension floats. So a rough estimate of a data set size for 100,000 reviews is roughly 100 megabytes of raw text. And the embedding is roughly 300 megabytes of data. So what are some of the building blocks that we need to build this system that needs to search across 100,000 product reviews? So first, we need a text data store, right? So this is where you're going to be storing your source data. So in our case, our 100,000 reviews. And this is going to be used for rendering results and also mapping the embedding results back to the original text. And the next thing that you need is an embedding generator, right? So this is actually the component that turns your review into a dense vector. And this is going to be using some type of pre-trained model, like Expert, OpenAI, whatever model that you want. And this is how you're going to be capture the semantic of your reviews and return relevant results, rather than just returning back raw keyword search results. And the next thing is a vector index. So this vector index is where you're actually storing your embeddings, right? And here is where you're going to enable some type of nearest neighbor search. And that's going to return you the most relevant embeddings for the search query. And finally, you need some type of a query layer. So this query layer is where you're going to be accepting the user's query and then try to embed these queries and then run the nearest neighbor search and then finally return the results back to your user. And this is a layer that allows you to sort of make your system interactive and usable by a human or some other systems. And that's it. I mean, you can build a simple semantic search system with just these 4 foundational components and without any need really at this point to distribute anything. But the reality is, oftentimes, when people hear I'm using embeddings, that means I need a vector database. Or simply, I need to build this system for future scale that's going to arrive. So instead of using CSV, SQLite Parquet to begin with, they go for S3 plus Iceberg. And for embedding generation, instead of using Torch and Hugging Face and start with local training and generating, they go for Ray, Dask, or Spark. And for vector index, instead of trying out DuckDB or FICE, because I don't know if FICE is too opinionated perhaps, they go for Pinecone and Weaviate. And the query layer, instead of just using a very simple, fast API and Flask that can scale to hundreds of concurrent queries all at once without much trouble, if you know how to actually do it correctly, people build microservices running on Kubernetes. So what happened here is people are building for the scale and trying to solve a problem that just simply doesn't exist yet. You don't have the scale just yet. So you traded local simplicity for a system that is completely premature. And instead, you're paying the new complexity tax, which is basically a combination of coordination and debugging overhead. So these two systems, imagine they both give you 100 milliseconds of latency. Which one would you rather maintain? Right. So the next time, if someone claims we need a feature store. Maybe first ask, how many features are we talking about, right? If you have 3 features, maybe consider using a CSV. Or even more features, maybe a CSV is good enough for a long time. If someone's asking, we need streaming to generate embeddings, maybe ask, how frequently are your documents actually getting updated? If your documents are static or are getting updated very infrequently, you don't really need streaming. Perhaps you can just use a for loop, and then that solves the problem for a long time. You don't really need a Kafka producer to publish doc updates, Kafka consumers to batch and embed these updates, Redis clusters to store intermediate results, and some type of monitoring to deal with failover recovery. And if someone says, we need distributed training, maybe think about how big that training data really is and how big the models are that you're actually dealing with. Because for 10 million parameter models, that's around 40 megabytes in float 32. And you can fit dozens of these on a single CPU or GPU. So you don't really need distributed training. And if you decide to actually train things on multi-node, you will have to deal with that coordination overhead in the multi-node scenario as well. Training these things on a single node machine probably is going to take hours or days, hours or minutes, not actually days, right? So basically, what you want to try to avoid is spending more time on managing systems communication as opposed to doing the real computation on your system. In fact, I will go as far as to say that 80% of teams are using less than 10 gigabytes of data sets, pre-trained models, and CPU inference. And why do I say this? So let's look at it one by one. Less than 10 gigabytes of data. Most companies actually don't have that much labeled data or structured data. Let's look at a few examples. 1 million rows of CSV is between 100 megabytes to 1 gigabyte. 100K user reviews or support tickets is around 100 megabytes, raw text. A few thousand product descriptions, articles, resumes is still less than 1 gigabyte. And even for larger types of data, like PDFs, metadata, whatnot, that's still most likely less than 10 gigabyte in general. So, and the kind of AI workload that this type of data size can support includes search retrieval systems, classification and ranking, and fine-tuning small models. So that's pretty powerful. And I believe that most teams are using pre-trained models. Why? Simply because they're faster, cheaper, and proven. And there are so many of them available out there that you can use, like BERT, DistilBERT, MiniLM, OpenAI embeddings, Whisper for speech, Clip for vision text, and sentence transformers for semantic search. Really, most teams just need to embed data, maybe do some type of zero-shot inference, and they're not actually training models from scratch themselves. And why CPU inference? Again, it's cheaper and easier to scale and easier to deploy. You do not need customized runtime to deploy CPU. Even in production, most workloads don't need GPUs for inference. Unless you actually need real-time vision, speech, or LLM at high scale, GPU is not going to be super relevant in those cases. In fact, on Hugging Face, most model downloads are pre-trained models less than 200 megabytes. Most Kaggle datasets are less than 1 gigabyte. And most companies are embedding, classifying, re-ranking, summarizing, instead of training models themselves. So in other words, most teams don't actually have big data problems. They have 8 gigabyte problems and 200-line model scripts wrapped in a 12-component distributed system that they copied from a blog post. And why is that happening, right? So what's actually happening is that systems are distributed before they're actually useful. And a lot of it has to do with resume-driven development. So people really want to put that cool technology on their resume and want to talk about how they were able to wrangle a distributed system into shape. And as a result, you have premature complexity for future scale that never arrives. In fact, for all the AI builders out there, before you build a distributed feature store, maybe consider some of these questions. First, do you really need it? Can you batch, cache, compress? Can you pre-compute, run it offline? Could it fit in DuckDB, SQLite, or a columnar file? And perhaps use a checklist like this. Will this serve more than one model? Are you retraining continuously? Is data freshness mission critical for you? Are you multi-tenant or real-time? Are you scaling to billions of rows? If your answer is no to most of these questions, you just need a CSV probably and a good join optimization strategy. You don't really need a vector database. Sometimes the smartest scaling move is actually to stay on one box. But I'm not saying that all of the AI workloads do not need horizontal partition type of scale out. Some do. So for example, if you're actually doing model training for LLMs, like if you're training GPT-4s from scratch, sure, fire up that cluster. If you're working on real-time robotics and vision pipelines, where you're dealing with petabytes of logs per day that's getting generated, yes, maybe you'll need Kafka. And if you're working on a system that's large-scale embedding search across billions of vectors, yes, I think you will need a vector database. Because at that point, you're not really just storing embeddings anymore. You're building a complete full search system that needs to deal with latency and feature complexity as well. And when these happen, it's going to be very obvious to you because these are rare and you will notice. But if you're just building a semantic search system for 100,000 product reviews or blog posts, why are you trying to get a vector database on a Kubernetes ingress controller? There's no need for that. Local systems still win. Systems like DuckDB, which is a single binary and is blazingly fast and can handle many, many different types of workload, is very popular. And the cloud version of it, which is MotherDuck, scales DuckDB, but without distributing by default. SQLite runs everywhere, on your iOS device, Android, browser, application, and it's very powerful. And if you use PyTorch plus a good CLI script, you can probably get started with more than 80% of ML workloads. So, simplicity is your superpower. 10 engineers plus Kubernetes plus 6 months of development time might give you 100 milliseconds of latency on your system, but 1 engineer plus DuckDB plus batch cron job can probably give you 100 times the performance improvement at 1/10 of the cost. What I'm trying to say is, scaling is not the same as distributing. What you should be doing is to squeeze out of that one machine as much as you can before you skip ahead to split your workload across many, many machines. Before you scale out, try to scale right. Because some of these strategies that you're going to be employing on a single node machine is going to be just as critical when you scale your system out and when you go distributed. Let's talk about a few common strategies here. The first one is multi-threading, right? So basically, you want to be able to use all of the available resources, threads, cores on your machine before scaling out. Because when you do go distributed, each of your node is still supposed to be multi-threading very efficiently. Otherwise, you're just distributing inefficiency. In fact, a single 32-core machine can be very powerful. You can run hundreds of queries in parallel per second. You can deal with models with 1 million plus embeddings, and you don't have to worry about anything related to coordination overhead or network complexities. The next thing is try to pre-compute and cache, especially for large, expensive results like embedding and joins. So you don't have to recompute all of that results. When you go distributed, recomputing is going to mean having to deal with cross-node communication. And that's going to be expensive because you're trying to coordinate across your cluster. And that's going to increase your network usage and lead to network saturation. And you don't want that. So in some ways, caching is even more critical and matters more in the distributed sense. And you want to get that right on your single node machine first. And batching is another good idea. Run tasks in parallel can make sure that you're not oversaturating your RPC or network. And when you do go distributed, the same theory applies. You want to make sure that you're leveraging the task coordination correctly, and you're batching and you're reducing the amount of network traffic so you're not saturating your network unnecessarily. So these strategies are not different when you move from single node to a distributed system. So what I'm trying to say is really this. A well-architected single node system isn't an alternative to distributed. It's the foundation for doing distributed sanely. It's not like you're picking one or the other. I'm going for a single node or scaling vertically, or I'm going distributed and scaling out my system. It's not one or the other. You're not doing something different when you actually do go distributed. I like to think of it as this. Building a single node system is when you start to understand the shape of your system. And building distributed system is when you scale that shape out, and hopefully not breaking the system while you do that. In the end, how you scale depends a combination of workload, the bottlenecks that you see in your single node system, and the trade-offs that you're willing to make. Believe me, it's a lot easier to fix kills on one machine compared to 100 machines all at once. And that same problem is not going to change just because you have done your horizontal partitioning. So I'll be talking more about this later this year at the Systems Distributed Conference in Amsterdam. So if you happen to be going there, I'll be continuing this discussion. Thank you.